Domain of rational functions. Now, this topic is technically one we've already talked about before, finding the domain of a rational function. However, it's part of a larger discussion that we're about to have about rational functions. So, as a reminder, what is a rational function? A rational function is a function where both the numerator and the denominator are polynomials. So, anytime you're seeing x in the denominator and well, I mean, I guess it has to be a polynomial, but anytime you're seeing a polynomial in the numerator and denominator, in particular the denominator, that's a rational function. Now, we've talked about graphing polynomials. We did that a few sections ago. It was a lot of fun. Y'all enjoyed it, I'm certain. And now we're going to get into graphing rational functions. And rational functions just have a lot more properties than polynomials do. There's a lot more to talk about. There's a lot more nuance. So we're going to start this discussion on how in the world do we graph these by talking about the domain. Again, something we have talked about before. The domain of a rational function is going to include all real numbers except those that make the denominator equal to 0. So to find the domain of a rational function, you're just taking the denominator, in this case x plus 5, and setting it equal to 0. And then you'll get that x equals -5 cannot be in the domain. So we want to take -5 out of the domain. If I look at a number line, because I like to look at number lines, and I plot -5 right here, we're trying to just exclude them. So we want all of this, we want all of this. So from -infinity up to -5, and then from -5 to infinity. So our domain, in interval notation, -infinity to -5, pluck -5 out. That's why we're using parentheses. -5 to infinity. We'll do another one. Taking the denominator, setting it equal to 0. X squared minus 9 factors into x plus 3 times x minus 3 equal to 0. Setting each of these factors equal to 0, you'll get -3 and +3. These are the excluded values. These are the values we want to exclude from our domain. So I will draw my number line. I'm going to mark -3 on here. I'm going to mark +3 on here. We're going to go ahead and just take those on out, pluck them out. And you can see that this separates my number line into 3 distinct pieces. So when it goes into interval notation, there should be 3 distinct pieces, just like there were 2 distinct pieces up here, and we had 2 pieces in our interval notation. The one that students will forget about the most is this little portion right in here. So the domain of this goes from -infinity to -3, union, plucking -3 out, -3 to 3, that's this portion here, and then union 3 to infinity and beyond. And that is the domain for this guy. Just one more example, keeping this video nice, short, and sweet. Factoring x cubed plus x, we can take an x out. We get an x squared plus 1. X squared plus 1 does not factor. This does not factor. It only has complex zeros, and we don't need those here, not for graphing. If we let x equal 0, then we get that we need to take 0 out. And it makes sense. Think about plugging 0 into this. You would get 0 divided by 0. We don't want that. That's not something we can handle. So just like we've done before, come on, Mr. Line. There you go. Plucking out 0, take him away. From -infinity to +infinity. Our domain is -infinity, pluck out the 0, from 0 to infinity. Now, special things are going to happen at these places where we have domain issues. remember with polynomials, you drew your graph and it was just like boom, ba boom, ba boom. There was no domain issues. Something happened the entire way. When you have a domain issue, that means there's a place on their graph where there's an x value that doesn't have a y value. So what is happening at that x value? Well, good news. We're gonna find out. So tune into the next video and I'll see you there. Bye.